Hello everyone, I'd like to take this opportunity to welcome you all to this Thursday afternoon presentation session for the finalist presentations for the Foundation Prince Albert II of Monaco Award and the Innovation Prize Tech Talks of the Monaco Energy Boat Challenge 2026. This afternoon we will hear from the finalists of two very important awards, and we will begin with the Foundation Prince of Albert II Sustainable Yachting Technology Award. This award recognizes and supports outstanding sustainable yachting technologies developed by universities and research institutions. The finalists will present their projects to the international jury, with the winning team receiving a €25,000 research grant to help their solutions move forward towards real-world implementation. Before we begin the finalist presentations, I am very pleased to welcome Salomé Montmartin to the stage, the Polar Initiative Manager at the Prince Albert II of Monaco Foundation, to say a few words. Thank you.
Hi everyone, thank you for being here today. And thank you for presenting your innovation. So I won't be too long because we have 4 teams that we're looking forward to hear from. But as you heard, the FPAII Award was created in order to help scalable solutions, so to help move university to move from prototype to scalable solution. We're looking forward to hear from the 4 finalists today, hear how their innovation that they have to show us will transform the industry and how they're managing all the aspects of the industry to make their innovation scalable. So thank you so much for being here, and with that, I'm looking forward to hear to the finalists their pitch, and thank you.
Thank you very much, Salome, for the words and the explanation of the importance of the Foundation Prince of Albert and the work you do. To start, we will commence with the previous award winners of the Foundation Prince Albert II Award of the last year. This is Compéteur. So could I welcome to the stage? Thank you.
Good afternoon, everyone. Thank you for hosting us for the 3rd time on this beautiful stage. I am Jacopo Roncuzzi, the co-founder and CEO of Compéteur. What is Compéteur? For those who don't know us yet, it's the first electric outboard motor with counter-rotating and tractor propellers that we patented. The core technology is included, which is the counter-rotating propellers that allow for 16% more efficiency in propulsion. Let me talk a little bit about the business development. We were born in this competition. We designed the motor to win this competition. Last year we won not only the competition with 2 different boats, but also the Prince Albert II Award. So here we are, and in the last 12 months we were able to develop the business thanks to the help of Monaco Tech Incubator. And last month we established the SARL here in the Principality of Monaco. And our aim is to develop our business from here, to bring investors in Monaco. So I have this excellent news that we were able to close the first investment round of €600,000 that will help us to develop the business in a very rapid and fast way. We have an 8-people team, which is very heterogeneous, and we cover all the parts that help us to develop not only the technical part, but also the financial and legal and tax part. We are starting selling our first units in 3 different market segments. The defense segment is the segment which is more interested in our solution because of undetectability features we have. But we don't leave behind the mass marine market. We are building work boats, electric work boats for marinas and natural parks around Italy. And the luxury market. We are aiming to sell the first luxury tender in 2027, which will be able not only to go around full electric, but also to be the power bank of the yacht. Thank you. Now I leave the floor to Professor Nicolò Cavina, which is our president.
Thank you, Jacopo, and good afternoon to everybody. Now that we have introduced what Competitor is in terms of business development and startup, let's take a closer look to the Prince Albert Award that we gained last year and why it is so important for us. Because essentially it allowed us to invest some funds and some energies into a parallel direction that goes into developing components that reduce essentially the footprint, the carbon footprint, the energy footprint, specifically for marine applications. So last year we proposed a project that would go into 2 different directions to achieve such objectives. One of those was to essentially substitute as much as possible the most energy intensive material that we use in our solution, in our product, that is carbon fiber, with natural fibers and thermoplastics or thermoresins. On the other hand, we proposed the idea to develop batteries that are based on sodium rather than ion lithium. And that is, of course, to reduce the carbon footprint, if you want, and to achieve a product that has specific advantages for marine applications. So I will try to give you some, let's say, insight of what we have done. I'm sorry, but our CTO, that is the real technical expert of the natural fibers, is racing right now for the speed race, so I will try to be as clear as possible with my limited, let's say, knowledge about the specific topic. Then I will leave the floor to Stefano Patassa to describe the process that we did for sodium batteries and the switch from lithium to sodium batteries. Before starting to go a little bit deeper, we can say that we achieved what we proposed. So we really did some R&D on both those aspects, and now we are in the prototype phase for both both the materials and the batteries, and we can show you some components that are right here and that we're using in our boats right now in the harbor. First step, so the first idea was to investigate more and develop components that are based on flax fiber rather than carbon fiber. What is the reason for that? Of course, it's an attempt to reduce the carbon footprint and the impact of our products in terms of CO2 emissions, first of all, energy usage also, but also to try to, let's say, build upon the performance improvements that such materials could allow us for marine applications. In fact, flax fiber has a very significant characteristic, that is the ability to dampen vibrations much more than carbon fiber, and for marine application this could be a very interesting content, and more than that, it eliminates sharp and hazardous shattering when the material fractures, and this could be another significant advantage. On top of that, of course, it's the reduction in CO2 emissions that we calculate in about 35% for the pure material. Then the idea was to use thermoplastic, and essentially we used a new resin. This development was done in collaboration with NL Comp, a startup company based in Italy that has a great expertise on such materials. And therefore, we found out that we could use a process that would be much less energy intensive, because essentially we could use room temperature resin infusion rather than autoclave processes. The ideas were good from this point of view, but I have an issue with the pointer. I don't know, it's not working anymore. I'm sorry about that. Anyways, I was going to show you, but I hope it will restart. Okay. I was going to show you exactly the fact that the idea was good, the numbers were good, but then the process was complex. So we essentially encountered a problem because the process of using flex fibers would increase essentially the thickness to achieve the same resistance. And therefore, we introduced a new hybrid layup solution in which we still use some carbon fiber components in a very limited amount to provide the same stiffness with a much limited thickness. Where are we now from this point of view before going to the battery side? We have essentially a steering plate that is fully built in flex fiber rather than carbon fiber. It is actually operating on our boat, and this component can be considered fully completed. We are still in the validation phase of the rudder, which is the one you see there. So the point is that this is the most stressed material from a mechanical point of view, so we're still testing it to see whether we can really achieve the same type of performance. The next step could be a full hull made of natural fibers that we are developing together with a partner. I leave the word to Stefano Patassa for the battery part.
Thank you, Nicolo. And good afternoon, everybody. I'm Stefano Patassa, I'm head of electronics at Competitor. So last year we proposed to do sodium battery pack because we believe sodium has very key advantages compared to the technologies that are used now in marine sector. Those two technologies are lead acid and lithium. Both of them have some disadvantages that we don't really like on a boat. So the lead acid contains lead and sulfuric acid, so it's a bit of hazardous materials. The lithium has well-known thermal runaway and fire problems, so that's something that you don't want on a boat. We believe sodium can solve these problems because sodium apparently doesn't have thermal runaway and doesn't have the problem of the scarcity of the materials and the supply chain criticality. At the moment, we can start seeing on the market the very first commercially available sodium cells. The product is not really mature enough to make traction battery, so we decided to start from another aspect that is used in the marine industry, which is service batteries, so a 12-volt system that can be used right now. We have a prototype there as a replacement, drop-in replacement for service batteries in the yachts. We choose to prototype with a 12-volt system because it's, of course, much easier to prototype, which is smaller, and it's also less risky from a capital point of view. And we decided to do a drop-in replacement to common batteries, lead-acid batteries that you can find on your boat. As you can see here on the slide, I will be very quick, but we have similar capacity, similar usable capacity. But this battery, despite being a very early stage prototype, already shows incredible figures, especially the life cycle is outstanding compared to the competitors. And the pack weight, so it's the same size of a lead-acid battery, but it's one quarter of the weight. So that's the biggest achievement, and also it's a sustainable material, and it's not polluting and doesn't rely on the single source of supplies. Where are now? So we have this prototype, 12 volt. Where do we want to go? We want to go to build a smaller traction, lightweight traction battery, something that can be used, for example, in an energy class boat next year, maybe. And to gain experience on those cells, to work closely with our suppliers in order to be ready, to have experience, and when the technology will be mature, we can switch immediately to a proper traction battery for proper traction of a real boat. And that's it. Thank you very much for your attention.
Thank you. It was lovely to see the application of the award and how the Monaco Energy Boat Challenge can develop the different university projects into enterprises. Thank you. Over time. So now we will begin the finalist presentations of this year for the Foundation Prince Albert II of Monaco Award. I would like to start with Foil Sense, an open foiling platform by the University of Genoa, Elettra Unigi.
So, good afternoon, everyone. So I'll try to explain you what we mean for open source foiling. So as we know, foiling system can reduce the drag by lifting the boat from the sea. And I think that when we think about foil, we always think about fast boat, so both sailing boat or motorboat. So we think about performance, but reducing the drag means also to improve the efficiency. And so this can push the sustainability of the marine sector. But what is the main problem for the use of foil, especially on small boats, that usually they are designed together with the boat, they are complex, they are costly, and so this of course limits the possibility to use them, for example, on small boats. So what is our idea? Our idea is to try to find a way to make foiling system scalable and to integrate them in small boats. When I talk about small boats, I mean from 4 to 7 meters, 200 to 500 kilograms. So our goal is the energy boat class target. And of course, there are some limits for the use of foils. As I was saying, normally they are proprietary, expensive flight control system. They are, as I was saying before, it's difficult to integrate them in small boats, and there are also some aspects regarding regulations. So let's go inside our idea of open source foiling. So our idea is to provide an hardware kit with the foil and commercial sensor and actuators and a control platform that we can provide with a standard control and some guidelines to adapt this control to new boats. And so the idea is, okay, if you want to use the foiling system, you don't have to start from zero. You have this kit, you have all the sensor, you have a basic control, and then we provide you some guideline to tune your control, and of course it's open source. So you can also try your control without starting from zero. So the difference in comparison to what we have today is that this can be applied to already existing boats. And of course, to do that, this should be modular. And we are using in our project commercial sensors and actuators so that it can be easy to reduce cost and simplify maintenance. Where are we now? We have a prototype. We are testing it, and we are starting to do the first controlled flights. As you can see, we have pointer. No, we don't have the pointer. We have a foil. We have two foil actually that were custom made by a company in Genova, Italy. Is Verme Project, the name of the company, and then we have all the system with controls, with sensors, actuators, and we have a commercial control platform with the software. So actually, we have done. Okay, we have done the phase 1, and now we are in phase 2 and 3 because we have the prototype, but when something is not working, we have to go back to simulation. So we are jumping from 2 to 3. And then we hope, if we have some funding, to go to the last part of our project. The foiling system costs to us 30,000 euro, but we think actually it was the first prototype. We have more sensors that the number we supposed to have in the final kit. So optimizing all these aspects, we believe we can go ideally to 10,000, but something in the middle. And of course, today we have the foiling system and then the electric propulsion. Of course, it is possible to integrate the electric propulsion in the foiling system, also because I am an electrical engineer and I want something to do in this project. Of course, the cost of this depends a lot on the type of propulsion, type of boat. And then, of course, when we have finished, there is a lot to do to make this a standard, because we think we have to validate our simulative models on the prototype. Then when we have validated them, we have to make a lot of simulation to extend this to all other boats. Of course, we cannot test all the prototyping all the different boats, but we can validate models with one prototype and then try to extend this with simulation. And of course, we need some funding for this other last part, these guidelines, documentations, and explaining the customer how he has to operate to make this system work on his boat. So we are demonstrating on our boat, but we want that people can easily use this kit and this approach on their boat. We don't, do the market need foil or not? Of course, we were saying about the sustainability. Of course, if we reduce the drag, we can reduce fuel consumption. But today, we have also on electric vessel the problem of range. And if we reduce the drag, we can also increase the range of electric vessels. And this can be can help the spread of electric vessels. So our goal is ambitious, is trying to move from a single prototype to somehow a scalable standard. So thank you very much for your attention.
Thank you very much for your presentation. I will now open up to any questions from the public. Perfect.
Thank you, congratulations. Jérémy Lagarrigue, the chairman of the jury, and as always, I start this question, and I'm sorry if the question will be rude, but we are trying to give an award, so I'm obliged to ask a sometimes dirty question. In your presentation, I am missing two things. One, I need to see a market analysis. The second one, you are considering foiling for small boat. It looked like the small boats are easy, they can easily reach planning hull because of the small hull. So could you explain the max gain you have on a small boat for a planning hull compared to a foiling boat? And on top of that, if you answer those two questions, congratulations for trying to make it open source. That's really a need. So thank you so much and congratulations for that, and sorry for my question.
I was afraid they were much more rude, so so thank you for your question. Yes, it's true. We don't have a real market today, so it is something. But you want this price, but there is no market. So why are you coming here? But the point is that we don't have also solution for small boats. So our idea is let's try to do, and then let's try to see if there is the market, because if you don't have the market, you cannot analyze. I mean, it's difficult to analyze a priori the market. Regarding the second question, actually, as I was saying, it's not exactly my my expertise, but I think that we have to try to see what. I mean, it's true. We have to see. I think we have first to have a prototype that is functioning, and then on that try to see if which of the two possibilities they are more efficient. I think it's something we have to try. Of course, we cannot. I think that this solution can be used for small boats. So at least starting from small boats, because we cannot start to do prototyping on bigger boats. So maybe this is not the best target, the small boats, but is where university can start, because otherwise we cannot start. So I think, I hope we can see some good results, and then at the end we will see and we say, no, it was not good, or yes, it's working, but maybe the best application is for bigger boats. So I hope I answered to your question.
Mine is not a question, it's just a suggestion on the same area that Jeremy has just mentioned. There is really a necessity to move after the dream or the idea into a quantification aspect, because obviously you are talking about really decreasing the drag, improving the efficiency and consequently longer range and so on. But you need, even in your dream, try to get some quantification in terms of, because at the end everything needs to be economically sustainable also, consequently. So my suggestion is fine, nice, having a dream, but just trying to do immediately after, trying to make some quantification that after will be at that point refined during, but is essential to do it, quantification.
Thank you very much for the suggestion.
More practical question. If you manage to fulfill the two first questions. I'm a user. I buy your product. I install the foil on my boat. What about the cleaning? My boat is moored at the quayside there. I leave it all day, all year long in the water. What will happen with the foil being underwater all time long? I believe that.
Actually, all the actuators are outside the water. So all the motors and sensors are outside the water. So you just have the mechanical part of the foil inside the water, and in the all the critical part that move the foil are inside dry part. So actually, it's just the wing of the foil, which I think can be comparable to another part of the boat.
No, because we know by experience that
It is not true. Okay. So
the foil, the cleanness, the foil to be effective, efficient needs to be very clean, and the fouling is coming on my foil very fast with the water and all the life.
So we have to think about the self-cleaning of the foil or something like that.
Yeah, anti-fouling or something that would avoid cleaning, like most likely before every use, because definitely, I mean, very practical. But that comes only after the first two steps.
Yeah. Okay. Thank you. But we will take into account that. So start thinking also on this problem. Thank you very much.
Thank you for your questions, and thank you kindly for your presentation. So I would now like to welcome to the stage the Hydrograds team with the toroidal propeller sustainable yachting presentation.
So good afternoon, everyone. We are Antoine and Victor from the Hydrograds team from Arzimétis Engineering School based in Aix-en-Provence, next to Marseille in the southeast of France. And today we're going to present you the work we did all along the year on the toroidal propellers. So this is propellers that we definitely think will be the future of the thrust in yachting. And let's go. So first of all, let us explain why toroidal propellers will be a good idea. Current conventional propellers create cavitation. They create cavitation, and cheap vortices. Why? So cavitation actually is a phenomenon you can see here. And it is created when the torque and the speed rotation of the propeller is very high. This cavitation actually creates a loss of efficiency for the fuel, for everything, for the thrust. Loss of efficiency, they create vapor bubbles behind your propellers. And actually, basically, how to explain it simply, it is when you see the bubbles coming to the surface behind your propeller, behind your boat, this is because of cavitation. Also, another consequence of cavitation is the damage on the blades you can see here. So it damages the blades become less efficient, and after that, they create even more cavitation, and again. It's a bit like a vicious cycle. So, one of the solution is maybe modifying, editing the geometry of the blade of the propeller. And here you can see, for example, a propeller with a loop blade, as you can see. This loop blade, because she coming back on the trunk, you can see it easily. She has several benefits. First of all, the flow behind the blade is guided seamlessly, suppressing cheap vortices. All right. Also, the cavitation is significantly and sometimes totally eliminated. And we know this is a major source of energy loss. Also, we can quantify that the hydrodynamic benefits, so the hydrodynamic efficiency, actually, could be approximately up to 20%. So get back 20% of efficiency compared to a conventional propeller. Also, the noise is really diminished behind it, from 10 to 15 decibel of less noise in the water. So it's better for the submarine ecosystem. And also it reduces vibration, so you have better boat condition. And so if you higher the efficiency, you reduce the consumption of fuel, which is better, and also reduce CO2 emissions for the submarine ecosystem and for just the ecosystem in general. We based on some equations you can see here, some complex equation, taking into account like 15 parameters. This equation comes from a document in free access, but actually I like to read all our a specific technology, a new technology actually. There's absolutely almost zero documentation on it on internet. So we tried to work on this equation to make our own toroidal propellers, because these kind of toroidal propellers which come from directly this equation, no change. Actually, they are not adapted to every boat, to every engine. So we need to adapt it to our boat, to our engine, to race here in the MABC. So we'll let Antoine explain you how we will deal with it.
Thank you, Victor. So, as Victor said, we generate the geometry of the propeller based on equation that take into account 15 parameters. So the geometry is very complicated, so we cannot design it on a classic 3D software. So we developed a Python script that where we get a file and a point cloud. Then we can export it on CAD software, and now we can work on it and make it a volumetric object ready for 3D printing, and production. The difficulty in that is to stay close to the initial geometry to keep the valuable performance of the shape while adapting the shape of the blades to our needs. Here you can see four shape of blades that we developed with differences like the blade sections, the thickness, and the difference between two NACA profile, one symmetric NACA profile and one asymmetric. This is the one we choose at the end. And also the gap between the start and the end of the blade. Here is some of the simulations we make to calculate the forces and the moments on one blade for one propeller. Then we took all the results, we compared them, and that allowed us to choose the propeller and the shape you can see there.
So, as Antoine explained, we made plenty of simulation to test our model to see if it's valuable, and it was. So we decided to do a 3D plastic printing and to test it in real life. Why this procedure? Because it's the cheapest to have something you can use. And you use it at a small torque with a small speed rotation just to see in the first place if you have primary issues before going with a more expensive procedure of fabrication. So, all right, thanks. So for this model, you can see right here, it was made in plastic. So I did with a small, slow speed, and we were really delighted to see that it was working in real life. So we see really like no cavitation at all, even though it was a slow speed, no cavitation. The noise was really diminished compared to a classic conventional propeller, and the vibration was also diminished.
Then we tried to test our propeller at an higher speed, but we had only a 3D printed model in plastic. So the propeller broke, but the broke was mechanical and not hydrodynamic, which is expected at this stage of the development of the product. We saw that even at higher speed there were no cavitation, less noises and less vibration, which was a very good point. So the design principle holds. Thank you. If we win the award, we would like to continue the simulations to test every shape of blade that we designed on the open form to the hydrodynamic part, and then on the ANSYS for the mechanical part. We would like to manufacture some propellers with these materials, with a different shape of blades, to test them at an higher speed that we test at the beginning, with the best shapes we will get during the simulations. This is laser sintering, sorry. And then at the end, we would like to manufacture the best shape we will have with metal by a foundry manufacturing, with the manufacture of the mold and lost wax patents, enabling the production of difficult geometries. Thank you.
Thank you very much for your presentation. I will now open up for the questions from the jury. Thank you.
Good afternoon. First of all, thank you very much for this beautiful presentation. We understand that it's very complex to calculate this and model it. I have a question about the final objective. Is the final objective is to get it into this product into production? So if it is a yes, you might be aware that there is a patent existing on a similar product, which is shower propeller and wind propellers. So how would you contour this patent?
Yes, we would like to make the toroidal propeller product and with a production. And Shower Marine developed some propeller a bit similar, but the difference is with the shape of the blade. The Shower Marine propeller, the beginning and the end of the blade is in the same point of the propeller. Our propeller, we have a gap between the beginning and the end of the blade that allow a better efficiency of the blade while reducing as much noise and vibration.
So you think this tiny change will make the patent not directly available to your product?
I do think that it could help us to develop the product, especially in Europe, because Shower Marine are based more in the United States. And the difference between the two propellers are significant. So I think it will be great for our propeller.
Let's try it. Thank you very much.
Thank you.
Continuing the same question, because if you want to create a company and you are entrepreneur, having a sort of IP competition is always an issue. So let's speak about this company that was just launching this propeller in last September 2025, so last summer. You were here in Monaco with this toroidal propeller 1 year ago, so before they introduce their product on the market. Do you have a sort of analyze about your innovation compared to their patent for the US market in order to give an idea to the jury if it's relevant for us to give this awards or not?
We think that actually we just as a students, our main firstly our main goal was to optimize everything on our boats. So we thought of the propeller, and when you see that documentation, we said ourselves, okay, we tell ourselves, okay, you got something to do on this thing. And after, yes, we saw that Shower Marine developed so these propellers, and I mean, our goal as students to win this prize is to put money to try things, to maybe develop a bit more the toroidal propellers, and the goal of Shower Marine is just to commercialize it, to make a business on it. Us as students, I don't think we will really want to commercialize it on our side. It's just for, yeah, firstly it was for the MABC challenge, but now it's more than research and development of the product to see to how much we can increase the efficiency. Actually, it's really more in educational aspect than economic. Actually.
Just a suggestion, I think that among the benefit, you can have also the reduction of collision, because these propellers, compared to traditional one, has less surface. So you can investigate on the percentage of these.
Actually, there is not lots of differences between the blade surface, because the shape of the blade is a blade that go back on itself by multiplicating so the surface by 2, and with that we can put like it's this propeller is a 3 blades propeller, but we can see that there is 6 blades and six surface in contact of the water. So the difference is not so big.
Thank you very much for your answers to the questions and the questions from the international jury.
Thank you.
Thank you, everyone.
I would now like to welcome to the stage Polito H2Fly from Politecnico di Torino. Thank you.
One microphone. Thank you very much. We only need one. So what do I click? I just click this forward. All right. Good afternoon. We are Polito H2Fly team. We're from the Politecnico di Torino, and we're about to present to you our newest innovation. It is a self-cooled battery cell that uses a proprietary phase change material, and we call it the PCM cage. So, with NMC cells, they are very prevalent in the competition. Various teams are using it. They're very prevalent also in the electric market, as they have almost one of the best performance of all the lithium-ion cells on the market. But they come at a high cost. There's a serious risk of thermal runaway for lithium-ion, especially NMC cells. And in the case of a thermal runaway for NMC cells, the result is very often catastrophic. Also, during high discharge rates, this thermal runaway becomes even a higher risk, and also during high discharge, high temperature, is a serious risk for high aging of the cells, degradation of the cells, and a loss of battery life. So, this is what we came up with. Our PCM cage is a fully self-enclosed battery cell which allows to cool the cells at any point. It has zero parasitic power as the cooling system is fully passive, so every piece of energy in this cell actually ends up in the system you are about to use. With this system, you enable a high discharge rate of 2.5 C and upwards without any risk of a thermal runaway. So the PCM we are using is in a technical collaboration with Petronas Lubricants International. It is biodegradable, it is completely inert, it is made from biogranular material, so very environmentally friendly. By limiting the temperature of the cells, we severely increase the lifespan of the cells, as degrading of the cells is actually exponentially, not linearly. So for every 10 degrees more of temperature, the aging doubles. So how does PCM work? PCM uses the endothermic nature of phase change. The same way like ice cubes in a bath of water cool the bath of water to exactly 0 degrees Celsius, same principle with our phase change material. When the cells heat up, they melt the PCM absorbs the energy as latent heat, and the PCM absorbs it as a latent heat, which results in a flattened thermal curve. Since the system is auto-equilibrializing, when the temperature rises or more heat is generated, more phase change, more cooling, which results in a completely flat curve. In our case, 47 degrees Celsius, the melting temperature of our PCM. For the construction of the PCM, thanks to Roberto and his hard work, he was able to cut the construction of one of the PCM cages down to 20 minutes per piece. And we have a container which contains our cylindrical cells. We seal the container, and in the end, we insert the PCM by the way of heating up the entire assembly with a funnel. So the PCM liquefies, enters the PCM cage, and then re-solidifies in the PCM cage while it cools down. Afterwards, the PCM cage is sealed and is ready to go. So you might say, all right, I'm saying all of this, I'm just telling stories, but we have done both in-field tests and laboratory tests. For the laboratory test, we have done a discharge with one of the cells without any PCM and one with PCM at 240 amps. And the cell with 240 amps reached a whopping 63 degrees Celsius. That is a significant risk of a thermal runaway. Imagine this type of cell, closed box, sun shining on it, that I do not want to be around those cells. With the PCM cage, we expect it behaved exactly like we expected. The temperature rose and it just capped at the melting temperature of the PCM. Believe me, no matter how much I tried to overheat the cells, I was not able to. We have also those PCM cages installed in our boat. The entire battery is made up of PCM cages, and so far the PCM cage has never let us down. I was basically able to tell the pilot, step on the gas, go, and you will not have to worry about anything. So if we compare that to traditional cooling systems that act with a medium, for example, forced air or liquid cooling. Forced air and liquid cooling have significant drawbacks. Both, for example, let's say I use forced air. In a maritime environment full of salt water, debris, various materials I do not want to have in my battery. Liquid cooling, even worse, salt water. I do not want to run salt water through any type of battery. The PCM cage, no problem with that. You can just close the box and forget about it. The entire system is entirely passive, so you can just close the box and forget about it and have a nice day at the sea. We intend, with the money from the FPAII grant, to further develop the system and close the gap in the weight department and use more sophisticated material so it is more competitive. So we expect an evangelist market of up to 2 million euros in the field of small relaxation yachting industry, and especially in recent years with a higher push for especially also noise reduction legislation in Italy and France. There has been a push for more electric relaxation boating technologies, and, for example, have a conversion of a previous petrol-based boat to an electric system. This is enabled by the PCM cage, because you do not need to worry, okay, how do I implement the air cooling system? How do I implement the liquid cooling system? By building up the battery with those cells, the problem is solved. You can convert it to an electric boat, and you can have a nice day at the sea. So we have a patent pending on the system, and we intend to further develop the system in the next year, so we can have a more ready prototype with more sophisticated materials, with a proper market analysis, and have it market ready. So I would be very happy if you would come by at the boat, check it out. We are very passionate about what we're doing, and I would love to chat with you about it. Thank you very much.
Thank you for your presentation. I will now open up the floor for the jury if they have any questions.
Hello, I'm Andres with FPAII International as a naval architect, and my question is, I see your experiment goes up to 80 minutes and at a high discharge rates of 2.5 C. What if this was over, let's say, a dozen of hours and at a discharge rate of 1 C? Is there any benefits? And the second part to my question is, what's the weight impact, a critical thing for boats?
Yes, we have, so first I'm going to answer the weight impact part. So we are currently at 190 watt-hours per kilogram, and with the new development of the system, we intend to go up to 210 watt-hours per kilogram. About the 1C discharge. At 1C discharge, we still have the same principle of the temperature rising up to the point of the PCM and then capping out. This also increased the lifespan of the cells as the temperature is capped to a lower amount, and since the aging of the cells is exponential, if it still remains below the cap of the PCM, that severely increases the lifespan of the cells.
Congratulations, that's very interesting. But could you give us an idea, because my understanding is with the PCM cage or whatever change of materials, you can cap a limited amount of calories. Could you, by changing the PCM materials, adapting this liquefaction at different stages of temperature? Because we all know that most of the industry is going to LFP battery, so the optimum temperature will not be the same. Will you be able to adapt your materials to be in the correct range on the new batteries development?
Actually, yes. With our collaborators at Petronas Lubricants International, we have various PCMs in the Petronas Iona Thermobat line. There are various increments, and there are almost in 1 degree steps PCMs available. So whichever melting temperature or temperature cap you choose can be available. For us, in our case, we choose 48 degrees Celsius because it is the sweet spot, if you will, of temperature safety and also having a bit of a gap between the surrounding temperature.
Definitely interesting presentation. My question goes to money. What are just indication on the sustainability from an economical point of view? What are the economical impact of your device?
So the economical impact is that it allows a transition in the small boat industry to a more electric industry. For example, a PCM cage in material costs 80 euros, which brings us to roughly 250 euros per kilowatt hour, which is quite competitive. So it is competitive too. Our idea is to compete with the petrol market and beat it out.
I have a question. What's your PCM, what's your product make the difference from the existing PCM solution, which are kind of widely spread in the car industry?
Yes, this is neither a paraffin nor a salt hydrate PCM. It is made from biogranular material, which results in a way higher thermal conductivity. So when it liquefies, instead of becoming more like a goo like you have with the classic paraffin PCMs, it becomes actually liquid, which results in a very high thermal conductivity. Yes.
Okay, thanks a lot for your presentation, which is very clear. So congratulations first. But what about repairing, maintenance, etc., compared to conventional batteries with this PCM cage? And what about the recycling of all those materials in the end, at the end of life?
Good question. So as you can see on our PCM cage, we have a quick release system. So in case there's an end of life of the PCM cage, it can be easily replaced. Instead of replacing the entire battery, one individual cell can be replaced. For the recycling of the system, it is very easy to separate the components because I'm actually an environmental engineer. I study a lot about the recycling of materials. So a big part in it is the separation of the components. In this case, since the PCM is highly liquid in its liquid state, the entire assembly can be heated up so the PCM flows out. It can be separately recycled. The container can be removed and shredded, and the rest of the cells can be recycled like any type of lithium-ion cell.
Thank you very much.
Thank you very much for the presentation. And as for the patent is concerned, so you're developing it with your university?
Yes, it is correct.
And can you tell us a little bit more about it? What precise mechanism are you patenting?
Yes, the precise mechanism that is patented is, first of all, the combination of the materials, how they're used. Second of all, that an individual cell is inherently self-cooled and not the entire battery pack. So to keep the modularity upkept compared to other PCM cooling solutions, and also the insertion process with the new Petronas Iona thermobat line is novel.
And so who is going to own the patent?
Polytor is going to own the patent, but we can develop startups in various ideas like that in cooperation with Polytor in the proprietary startup incubator.
Thank you.
And one important question for the whole jury and for you, depending on your answer. If you won the FPAII Awards, you already answered that you will use this money to develop, but could you please go back on that slide and give a bit more details about the use of fund, about if you won the awards?
I think that is the hydrogans. Oh dear. This one, are you talking about this one or the
I
one
think
after?
that was the previous one. You explained that if you have the money, you will develop something else.
I think this one is. Yes, the idea is to develop more sophisticated materials, so more sophisticated 3D printing materials, and get the PCM cage in various other sizes, so it has more adaptation in the market depending on the user.
And sorry, something important. What will be the next step? So you will say, as your university, you will develop new materials, have a bit more of expertise around those PCM. But if you have to create a spin-off with the idea of patent on something, could you explain us a bit the idea of having a link in between developing a solution and addressing the need of the market?
Yes. So, first of all, the first step is, like I said, with new materials, get the weight down so it is more competitive to other cells on the market. Second of all, properly test how does it impact the lifespan of the cell and get actual and KPI on that fact. And then get it to a point that can be applied to more solutions.
Thank you. Thank you for your presentation. So I would like to welcome to the stage Team C-Sakti and the Sea Shield.
Before we begin, our innovation is also something very similar to what Polyton did, but with different materials, and I would like to talk about that as well. So, to the overall of how much ever accidents and fire hazards that has happened in regards to the yachts and boats, major of them is because of improper thermal management, and that is what we are trying to solve. And I am Reshma Sharif, and along with me is Danya, presenting the award with you all. The world is becoming more sustainable. When sustainability comes into picture, the vehicles are becoming electrifying. So when electrifying is there in picture, the battery becomes the main topic in it. But when we use the battery's efficiency, safety becomes a major priority in it. But we tend to forget about it sometimes. But safety is majorly important to us. And that is where we are playing our game. The most commonly known battery is lithium-ion battery in regards to the yachts and boats. Deal with the improper thermal management, there's an already existing solution of battery management system. What it does is that it cuts off the entire system when the battery tends to overheat. But that is what we are trying to solve. The boat will be stagnant when it is cut off entirely, which will bring danger to the pilot as well. What we are doing is that we are bringing a battery thermal management system that is, it will manage and standardize temperature along the battery while keeping the entire system running as well, so that the pilot does not get stagnant in the boat in the waters. we did a market analysis. Right now, the majority of the yachts and boats are powered by fuel, but right now there's an emerging of hybrid and electric vehicles, and they become our target group.
Diving into the technical part of the system, we all know we'll first look into the existing solutions and the problems of the existing solutions so that we can sort how our solution works for it. So the most widespread use of thermal management system is, of course, the liquid system. But the problem with the liquid system is that on a long-term basis, it will undergo leaks, or the wobbling of the liquid will be a problem. And as Reshma said, again, the existing thermal management system cuts off the system in order to secure the entire system, but doesn't keep the system working. So our product is a cell bracket along with the PCM that doesn't need any external source of energy to keep the system working. So our specific PCM used is paraffin along with graphite. So 80% paraffin is the PCM that plays the role, and 20% graphite is helping the paraffin be intact and without preventing leaks. So paraffin, of course, as the previous team mentioned, it will undergo solid to liquid change. So to keep the liquid intact and not to flow off or undergo leaks, graphite comes in. Graphite is helping the paraffin stay intact and not flow completely off. Next slide. We also designed our brackets. Our brackets are designed in such a way that the top and bottom is made up of fire-retardant ABS material, and the sides are made up of metal or acrylonitrile sheets that is helping the system be more conductive, and it helps dissipate the heat out of the system faster. This doesn't require any external energy source to keep the system intact. So being why paraffin, to answer that, our system in our battery requires 50 to 60 degrees of temperature to go to the highest peak, and paraffin exactly comes there. Paraffin melts exactly at the point where the battery reaches almost 90% of its temperature. So when the battery reaches around 45 or 60 degrees, paraffin plays its role. It absorbs the heat and becomes liquid. In order to prevent it flow, graphite plays in and keeps it intact. It doesn't let the paraffin flow off. This is our testing module. This is our empty cell. This one filled only with paraffin. This is with paraffin with graphite powder. And this one is paraffin with expanded graphite. Expanded graphite comes in when the structure of the graphite is improved so that a lot of paraffin can be held together, preventing it from liquid flow. One second. This is our CAD diagram of the module. Sides are given to fill in the paraffin, and the center is for the cell. This is our structural arrangement done by analysis. Today we brought in rectangular because it was easy for us to make in a short period of time. This one is more efficient in designing, and structurally it occupies lesser space. This is our testing results. First one with the empty bracket went around 60 to 65 degrees, and the rest of the three with paraffin. Paraffin here, it shows a little bit of leakage because it was just paraffin and it melted off completely. The rest two maintained a very good intact structure and showed about degrees of 20 to 23 degrees, and it did not go above 45 degrees when testing. Next slide. This is our module that we have put in, 4x4 battery with paraffin and graphite filled in. Next one. So, of course, we have to see what are the problems it is solving. First thing, it keeps the system completely intact, doesn't stop anywhere. It doesn't need any external source to keep the system intact. So, of course, it is saving a lot of energy. It is improving the battery life. And this also stops the manufacturing quantity needed for the batteries. Market targets. Mostly, here, since we are in the ocean, we target all the ocean people. Yacht manufacturers, even we also focus on the small people, fishing vessel operators, marine battery manufacturers, passengers and crew, and of course the environment. One more thing is that our system is financially sustainable. Paraffin doesn't cost much. It is, I think, 1,000 rupees or 10 euros per kilo. So it is also financially affordable. Next one.
So how is Sea Shield different? I would like to talk about in the business perspective. the main MVP is what I would call, is in the business, is something which is affordable, which is easily available, and paraffin is right there. It is very cost effective while also being easily accessible to everybody. So that is where C-Shield comes in, while also graphite, expanded graphite, I think everybody can afford all of those, and while also saying that our material, this PCM, can be integrated in also existing batteries. All we have to do is mix this and integrate this in existing batteries as well. So they have the thermal conductivity as well. So our future roadmap is that right now what we did was that, as I just mentioned, we did it in an existing battery so that we can test how good the PCM is working. So we want to make another 20 kilowatt of battery, expand ourselves, make it and test it. Along with that, we also want to get certificates, safety certificates, while also registering and establishing ourselves as a company. That is a roadmap. We're also expanding in a manufacturing unit, as I mentioned, in a 20 kilowatt of battery. So I'm hoping next year C Shakti will come up with this battery and will show you our innovation in our own boat. Yes, thank you.
Thank you very much for your presentation. I'll now open the floor for the international jury to ask some questions.
One simple and important question. You basically come with more or less the same idea compared to the previous presentation. If we are a jury, why do we have to vote for you compared to the other one?
So, sir, the main reason why we applied for the Prince Albert Award is that we are a set of students. We are, as I mentioned, we are just researching about it. We want to build more of it and establish as a company and bring into action. We want to contribute to the thermal management safety in the marine system, and that is the main goal of why we applied here. We want to establish as a company, we want to apply for the patent and all of those. And we as students, I believe we will struggle a little bit in that side. So we needed your help in regards of those.
So with regards to technical answer, I would like to answer that we have integrated graphite with it, and it will not show any liquid features in it, and will not provide any leakage or any drawback that was caused in the liquid cooling system will not be caused by us, though it has liquid features in it.
And in performance, our system can push up to 6C of discharge.
Yeah. We did a discharge testing up to 6C, and we are also capable of doing it until 10C.
What? Thank you.
Hi, thank you very much for your presentation. I have a question regarding the mixture between paraffin and graphite. I understand you've made many tests and many variations of this mixture. Do you feel like after a certain amount of cycles, like melting, solidifying, melting again, the graphite and the wax will separate, and then in turn the PCM will lose a bit of efficiency?
Sir, of course, any material will lose efficiency, but I guarantee it will last very, very longer, because graphite is made up of carbon, and we all know carbon is non-degradable. It is never reactive or degradable that easily. We all know all our materials are also made up of carbon fibers, which is very strong and not very reactive and not degradable. So graphite is carbon itself with structurally inbuilt different than carbon fibers. So they are purely carbon and not degradable, not reactive, so it can last ever. I can guarantee that. Only the retardation will happen because of paraffin.
So answer to this, so our PCM have 600 life cycle. So
and also, sir, to answer your question more, since this is something we have to mix it as a slurry and fill it up again and again, this can be reusable as well. I mean, not reusable exactly. We can make the paraffin and the wax again, and we can reuse it again. In the sense, when it is completely done, since it is cost effective as well, we can take it, we can make it as we can do it, and we can fill it up again in the battery.
Thank you. Thank you very much.
Thank you. Congratulations. I think in your presentation you also mentioned the
potential reuse of regular batteries. You want to get a bit more detail on this one?
So right now what we did as a prototype to test about how safe or how good as a thermal conductivity our material is, what we did was that in an existing battery, last year battery of ours, we took that up and we we made this slurry material and we filled it up with that. Instead of the liquid cooling system, we tried and used this to test how effective this can be. So in regards of those, when we tested more again, maybe we'll know how effective that can be. But so far, I'm sure this can be done, sir. And I'm sorry I didn't mention this in our presentation. I'll have to prove how the cost effective is. In regards to the rupees, a normal battery will be around 15,000, that is 150 euros. And if we add for the materials of paraffin and wax, it will be 300 rupees, that is nothing but 30 euros. So in addition of that is how much a battery will, the entire battery will cost. So it is cost effective as well.
I am asking the question, but I have people helping me to ask the question. You explain it, but another time we want to have a bit more clear the use of fund about these awards from FPAII. If you deserve it, could you please explain in details the way you use it and the link with your university? And we understood you want to launch a company. We need to understand the link in between the two.
Right now we are doing it as an incubator center. So the name Sea Shield is what we are going to publish it as a company. Right now we've actually registered it as a startup, but we will have to patent it in order to show it as a startup right now. We've registered it, but we need more proofs and papers of those. So we'll be establishing and commercializing this as Sea Shield company while expanding it. So why, again, the question is that why we applied for this award, if I'm not wrong, is that we want to expand the manufacturing unit while also having a bigger team to work on this. Because it needs lots of research. The materials need more efficiency to them. We need to expand it more as well. So for the team, for the manufacturing expansion and also commercializing our own project and bringing that back as a battery in our own boat. And that is why we applied for the award mainly.
So again, to answer to your question, the Sea Shield is incubated by our own institution. Yeah.
And question for the marine sector, not only for the battery. Do you have an idea about in which those PCM could be used, not only on the battery, but on some other parts for the yacht industry?
So right now, as we see in our world, there are more modes of transportation emerging as an EV vehicles. In two-wheelers, in cars, all of those are expanding in an electric sector as well. So maybe their batteries are also majorly known ones are lithium-ion batteries in those modes of transportation as well. So we can adapt our PCM materials in theirs also.
So yours is like in the yacht, apart from battery, whichever parts. So yeah. Anything that heats up, I think if you bring in a proper shield around the board object, design a proper object and fill in the PCM, I think it can help. Of course it can help.
So even in the engines of the boat, we can use it. Like instead of liquid cooling, we can use it. Yeah.
Sorry, sir?
Thank you very much for your presentation.
Thank you.
Thank you. I'll keep it.
So that now concludes the final of the FPAII Award presentations for today. And I would like to move on to the Innovation Prize. But a first quick thank you to all the teams that presented today. And we appreciate your dedication and your hard work towards providing these solutions. So for the Innovation Prize Tech Talks, to explain a small bit about the award, the prize recognizes a team whose project brings a new idea with strong impact, real viability, and the potential to shape the future of yachting. So I would be pleased to welcome Jérémy Laguerie, to say a few words before we begin. There's the International Jury Chairman. Thank you.
Well, as you can see, the level is quite high, and normally it's quite rude as a jury to take decision in between two projects, especially when they are the same project. So I guess we will have tough discussion tomorrow. That was for FPAII Awards, but on the innovation prize, you know, we will be smarter together. So thank you at least for being here, listening to your colleagues, but also trying to apply to this innovation prize, because the idea is really to foster the people to communicate on ideas on innovation, because the idea of this event is creating a community to push this industry in the correct direction. That's why we need your innovation, we need your ideas, and you need to be awarded. And it's an honor to be the jury to put you on lights, and I'm very looking forward to have a bit more details about the presentation we received, because I do say that some of the presentation was very accurate, some other was a bit less. So you have today the finalists, and very looking forward to see the kind of innovation. Feel free to always go in the details, share your ideas, and ask the question also to the audience. Mainly we ask the question as a jury, but the idea of those presentations is also sharing the idea with the other people. So if some of you have other questions and you want to have more details, feel free to ask questions. So thank you for that, and another time very happy and proud to be with you. Thank you.
Thank you very much, Jeremy. It's a pleasure to have you with us. So I am now pleased to start the Innovation Tech Talk Prize presentations with our first finalist, physicist Monaco Energy Boat.
Good evening, everyone. I'm Mattia, and he's Nicola from FPAII, and today we are here to present you our innovation of this year, an automatic trim control system. Basically, we started from a problem, so we wanted to have the best setup and the best configuration of our boat in every time and every condition of the race. And in order to do this, we started by, in the last years, using fixed trims. We couldn't allow us to change the trim angle of our motor during the races, and have the optimal trim angle only for a narrow range of speeds. Then we passed to some manual operated trim, which allowed us to change the trim angle during the races, but our pilot couldn't focus really the whole time. And there's also the difficulty of changing the trim and having the best setup and the optimal trim angle for the whole race. Thanks to some simulations, we saw that having an error into the trim angle bring to loss of speed and some wasted energy, and this would result in worse race results. And for example, in let's take the championship race. We wanted to have the trim down at the beginning in order to maximize the acceleration into the lift-off of the hulls. Then we wanted to trim up a little bit in order to reach the optimal pitch angle of our boat. And then during the curves, in order to have a better control and to prevent propeller ventilation, we wanted to trim down a little bit. And for this reason, we developed our solution. That is a real-time closed-loop control system, which allows us to move the trim autonomously without any action required from our pilot. Our solution is made by 4 main components. So obviously we have an electrohydraulic actuator along with a potentiometer in order to always know which is the position of our trim. Then there's a PCB into the motor, which allows us to read what the potentiometer gives and to control the trim in real time at every time. Finally, on the ECU, we have a GPS and a 6-axis IMU, which allows us to read which is the pitch angle of our boat in order to control the trim.
Okay, so to understand better how this system works, as Matthias said, we have two control loops inside the system. The first one is a very simple one. It just controls the angle of the motor. It has a potentiometer that reads the position, and then the error given is processed to a new information that gives the information to the motor to how much to open, how much to close. And this, it opens the motor, and it's inside a bigger loop, a control loop. The bigger control loop, it reads the attitude of the boat through a IMU and GPS, and that attitude is calculated and used to compare it with an optimal trim angle, an optimal attitude given a speed, and that the error is computed through the main ECU that gives a set point to the inner loop that changes the pitch of the motor, and through both dynamics it changes the actual attitude of the boat. So I know that like this is a bit difficult to understand how does it work, so I will show you a practical explanation. Let's say that our boat is sailing in normal condition. Then, from some reason, the bow goes down. It may be a different distribution of weight, maybe I change position on the boat. If the bow goes down, this is rarely read by our onboard IMU, and it detects it, and then it gives the control loop gives the command to open up the trim, and thus the boat dynamics brings back the bow up, going back to the steady configuration, and brings back down the trim to go straight. So to find out this optimal trim angle, we started out doing some CFD computation, some calculations with MaxSurf to understand how the hulls behaves on water. What is the waterline, what is the optimal trim angle for each speed, and all of that. And we found out that the drag curve is very nonlinear around the optimal trim angle. So the optimal point is a very narrow window of 0.51 degree to get the less drag. Thus, it's very needed an automatic control loop, because for our pilot it's very difficult to get that tight of a control on the trim. But then we dwelled deeper, and we thought, how could we do this without all this calculation and all these CFD time, which is not cheap and not very fast? We developed two algorithms. The first one is a perturb and observe, very simple. The boat goes straight, and the boat changes a bit the trim angle, and then if it's better, it keeps doing that. If it's worse, it doesn't. So it finds automatically the optimal trim angle for a given power. And then we develop a machine learning algorithm, which is a bit more difficult, and given some data points, it performs an interpolation, and it creates a better image of what is the actual, I can say, how actually the hulls behaves on the water, and so we get a fuller picture of that. These control loops are implemented in our own electronics. These are the two main boards that Mattia described to you earlier. We have the left one, is the right one for you, sorry, is very small. It delivers up to 3 kilowatts to the motor, to the electric actuator, and it enables the inner loop. The outer loop is enabled by our own ECU, which is the main control brain of the boat. And it has the IMU, GPS, and everything. And they communicate via CAN bus interface. And the ECU, it has on board an extended Kalman filter, which gives better output from just the IMU, combining the data from the GPS and from the IMU.
So basically, after we realized all the software and mounted the hardware, what we had to do was to validate the simulation that we have done before, and to validate also the Kalman filter and the other things. As you can see here there's the how our simulation went against how actually the actuator worked. So Yeah, and then other than this, we validated the extended common filter from the GPS and the gyroscope and accelerometers through some static trials at the beginning, and then with some dynamic ones. And from the result, the simulation, the actuator had to settle in less than 3 seconds, and actually what happens is that actuator settles in 2.8 seconds. So the simulations were pretty much perfect, and the outer loop pitch error was estimated into less than 0.5 degrees. So basically, we did an estimation in order to understand how an automated control could win over a pilot, let's say. And so we estimated the fact that our pilot could have an error of 0.5 degrees at the speed of endurance, let's say, and an error of 1 degree on the speed race instead. And more or less, the drag reduction, thanks to perfect setup and perfect trim angle due to our control system, is around 10%. Also, we could see that we have a faster maximum speed for our boat, and not only, also a fuel reduction if we consider the same speed. So basically, having seen the advantages of this technology, of this system that we developed, so a lower consumption, a higher range capability, and a higher maximum speed, we thought that to create a plug-in and a plug-and-play platform for another boat could be a really nice idea and a really scalable idea, both for racing teams or for small boat owners which want to reduce their consumes, for example, and for boat manufacturers that they want to collaborate in order to go along with this project. Thank you.
Thank you very much, team, for your presentation. I will now open the floor for some questions.
Thank you. That's very interesting, because we all know the control system for foiling, and as we are not foiling, having a control system to have the optimum pitch for the boat, that is smart, and that's really a need, because we see all these leisure boats are never using the engine as the correct pitch, so they are consuming too much. So definitely that's a need for the market. Something interesting I want to know, do we have a max trim to avoid the ventilation? Because I guess if you lift too much the engine, you know, the propeller can take air and you can create ventilation, and then you lose all the amount of energy you want to create. So do you have, in which way are you limiting this risk of ventilation?
So in our own boat, of course, we know the actual pitch in which the ventilation happens, so we limit via software the maximum pitch, so we don't get ventilation. In an, let's say, implemented system in a different boat, of course, it should be tested. And the first part, like the machine learning part, it should also interpret this, because if the even a simple software as the perturb and observe, if the motor is lifted up and it exits the water, we see a sharp drop of performances, and it's recorded on the system.
Okay, thank you. Another question: when you explained on the last slide the amount of energy you were saving, you were considering just the push, but did you integrate the consumption of the movement of the engine inside your calculation?
No, actually, in that calculations of the efficiency saved, it's not present. But if you consider the, let's say, the cosinus of the trim angle of the motor, what you are losing as in efficiency of the propeller and the propulsion is not that much. So I think you could, let's say, yeah, save it.
Do we have any questions from the audience? Any hands? Thank you very much. Thank you. I would now like to welcome to the stage Polito H2Fly.
Hello, it is, again, Polito H2Fly, again with the PCM cage. Under the risk to not bore you too much, I will go more into detail about the technical aspects of the PCM cage, as I'm very certain you would be interested in that. I'm going to gloss over the details, maybe for the people who have joined in later, of the basic principle of the PCM cage, which is a self-enclosed system we have developed in technical collaboration with Petronas Lubricants International that uses a phase change material to properly cool the cells at all times. And uses latent heat to absorb the energy and turn it from solid to liquid phase, and thus absorb the energy as the form of latent heat. So, the problem we faced was our NMC cells that are highly powerful. To be exact, we use 10 power 50 XG tabless cells. Those tabless cells are an internal resistance of just 700 microohms. So that is quite low, which results in less heat generated. But in case of thermal spikes, high discharge, we have still our PCM cooling system, which allows us to fully enclose our PCM cooling system and our battery pack inside a box to avoid any salt water entering, any gunk, any goo that you would not like to have inside your battery cell. So this is entirely passive. You have no extra cooling system, no parasitic power, and no external power needed, and also no control systems. So every energy that is in this pack actually ends up in the system you're about to use. For the recyclability, as we said, the PCM we are used from the Petronas Thermobat line is biodegradable, and it is from a biogranular material. So we can recycle it, we can use a separation technique in the form of heating up the PCM cage to remove the PCM from our PCM cage, and then later remove the other parts. As you can see, Roberto has a model with him. This is the inside of the PCM cage. You have the various cells connected in series with a copper bus bar attached to all the contact points of the PCM, of the tablet cells we have in there. So, what is unique about this cooling system compared to a traditional cooling system with liquid or forced air? As we are not using a medium to transfer heat away from our cells, we're using latent heat to absorb the energy, which is then later on radiated off passively when the PCM resolidifies. And we have done our tests. During our test, the charging phase was always sufficient for the PCM to recuperate, fully solidify, and always ensure that the PCM is ready to go and is able to cool our cells even after long periods of use, long discharges, and high thermal spikes. For the construction of the PCM cage, we have 3D printed a PETG container. This PETG container was chosen because PETG has high structural reliability. It is able to absorb the thermal power or the thermal surrounding temperature when we put the entire assembly in the oven, as it has a heat deflection temperature of 70 degrees Celsius. And because of PETG, which is very easy to use as a sealing container, as it can be printed very precisely, which allows us to properly contain all the PCM inside of the PCM cage. Because the PCM becomes highly viscous during its liquefaction, we had the risk of the material actually diffusing through the material. So we had to spray the insert with latex rubber spray to ensure a seal at all times. We connected the ridges with silicone to ensure a seal, and then reinforced the PCM cage with an epoxy resin. So at all points, the possible failure envelopes are protected. For the proof of concept, as we have said, during high discharge rates, we were never able to go above the melting temperature of the PCM. The temperature has risen and always capped at the melting temperature of our PCM, in our case 48 degrees Celsius. For the technical feasibility, as we said, 250 euros per kilowatt hour and 190 watt hours per kilogram. To add on top of that, if we calculate the kilowatts per euro, this one has a maximum discharge rate of 1.7 kiloamps, so we're able to draw a lot of power out of one of those cells, which put into numbers, we are talking about roughly 13 to 15 euros per kilowatt. This has been installed in our boat. It is fully operational, and we have also a few spare packs that in case we have any faults, we have any degradation, we can just replace it at any point. For the market potential, since we said we have a patent pending for the PCM cage, we intend to get it market ready within this year and get revenue also within this year, and do it in cooperation with our university and also our startup incubator, I3P, and create this plug-and-play system so we can reach users within this year. On top of that, we're applying to the Intesa Sanpaolo grant. This one will grant us to develop the system even further and properly turn it into a startup that is in cooperation with our university. As for the scalability, we also intend to automate the process even further to ensure that more sizes of cells are available. They can be produced in a highly, in a quick way, so we have a reduced time of production and automate the process as more than it actually is, including the PCM insertion process, and get it to a market-ready, proper product within this year. Thank you very much.
Hi, thank you for your presentation. I will now open the floor up again for the jury.
Are you aware of any standards that you must meet to commercially sell lithium-ion batteries with your PCM material?
Yes, we are in close contact with various stakeholders from the industry that are aware of those standards we need to comply with, and we are in constant collaboration with them, and this is what we intend to achieve within this year. For example, with our lawyers at the patent, with our patent lawyers, they advise us at all times so we can achieve those licensing.
One question that we forgot and we just discussed with the jury, do we have an analysis about the life cycle, about the material you are using, the PCM?
Yes, the life cycle of the cells is 500 cycles, but...
Not the cells, yeah, the material, yeah.
Yes, I was aware, I was about to go to that. The Petronas thermoband line, we have been assured that the life cycle is very stable. The Petronas PCM is highly chemically stable, and the chemical stability of the Petronas on a thermoband line will outlast the cycle life of the cells.
And excuse me, my life cycle analysis was the amount of CO2 to, I don't know, for 1 kilo of PCM, what's the amount of CO2 emitted for the production and after to recycle this material? You know, to have the overall life and the amount of CO2 emitted during the, if it's a good product or not a good product, basically.
I am very confident in our partners at Petronas that they have that are keenly aware of the CO2 cycle, and they have assured me that the CO2 cycle is within a reasonable range and competitive to other PCMs on the market.
Thank you.
Just a question about the design of your box, because it's part of your product. Why square, as the stacking of batteries is not squarish, but a bit like parallelogram? Because there is additional material in the corners. Does that make extra cost?
Yes, that is true. The design of the square material was for the ease of stackability. So it can be easier inserted into our proprietary stacking system in our boat. However, it is perfectly feasible to also with rounded edges. It is simply a choice of design for particularly our boat, but it can be modified.
Thank you for addressing additional topics in the second presentation. And about industrialization, where do you think you're going to put your factory or the 1 hour process to create your product?
As we are based in Torino, there's a lot of industrial capabilities, and we are very certain that I3P, through I3P, we can get into contacts with various suppliers and also within the industrial capabilities of the place that is Torino.
So you're going to subcontract the manufacturing?
That could be a solution in the future. For now, to get it market ready, that is a process for the future.
Thank you.
Would there be any other questions from the jury? Oh. And to the audience?
As you come twice on the stage, I have the opportunity to have this question, which is a very impressive use of emission material. Actually, you mentioned in probably the last slide, you have the other part of the cycles when you have the exothermic reaction for the solidification, and you say that the heat seems to wait out, which is fine. I just wonder if there is some case in which this could be a problem. For example, if you have a very quick use of the battery and then a very quick charge immediately after this event, this release of heat can interfere with the charging procedure or not. Because, and the other question is the enthalpy of transformation of phase change material. I mean, which is the amount of energy that you actually store for each degree of change.
To answer your first question, actually the heating of the cells actually assists in the process of charging the cells, as during high temperature, the internal resistance, when they are in this stage, decreases, so we can charge even better. And we have made the experience that a safe charge, which is usually 0.5 C, is enough time for the entire PCM to recuperate. So when the batteries are full again, the PCM is fully solidified and can be used again. As for the, excuse me, the second question? The enthalpy, yes. So the enthalpy of the PCM is roughly in the higher range of PCM. So we're talking about between 200 and 300 kilojoules per kilogram due to NDA. There are some restrictions, but during this charge, we were never able to melt more than 50% of the PCM that is within the PCM cage.
Thank you very much, and thank you for the questions from the audience. So I would now like to announce to the stage InnoBoat Bizkaia, sorry.
Hi everyone, my name is Yone and this is... Hi everyone, my name is Yone and this is Naroe, which is my teammate, and we are part of Innoboat Vizcaya. This is our second year participating in the energy class, and we are very excited to explain you the things we have been innovating this year. So first of all, Naroe will explain you our simulator, which acts as our digital twin. In second place, he's going to tell you about our pathfinding system. Later, I'll explain you the AI assistant, whose name is Agustin. And finally, we will tell you about the bioinspiration we took for optimal structure.
Hello, everyone. My name is Naroe. Last year was our first year, and we quickly realized that we had to implement a telemetry system that would let us know what our boat was about to do. But we also knew that it wasn't enough only knowing what the boat would do, but that it would be important to see, like, to have a telemetry of the field where we would be racing. So for this reason, we have implemented a route planning algorithm that has access to in real-time currents on the actual racing field or stadium that goes together with a telemetry simulator. So we can in constant time see what's the best path that uses currents to follow a more efficient route. To make it secure for the competition, we have implemented also an AI RAG agent that informs constantly the pilot where he has to go. For the pathfinding algorithm, we have used the Copernicus Marine Service, from which we download a NetCDF data, and we can choose not only time interval, but also location to keep it simple for the inboard telemetry. And this NetCDF data actually has different resolutions. So here we can see the classic A-star pathfinding algorithm equation, where we look at what neighbor would be the following one to make the route optimal or to be the easiest to get to. Since, as I've just said, the pathfinding algorithm and the data has a variable density, we have to pass it through a spline interpolation to make it feasible for the boat to follow. Here we can see an actual representation of what we managed to get from the pathfinding algorithm. We have selected some random waypoints, selecting a route. And then here would be, the blue points would be the data downloaded from the Copernicus Marine in real time. And also we have the capability of doing it with forecasting. So forecasting the day before of the endurance race, especially what the boat would do with the currents there are on the actual field. For the simulator would be the other big part we've implemented it. We have some input data that would be the desired path to follow and the desired speed. That this go through a PID control that controls the throttle and rudder input and fits the dynamic engine. This dynamic engine takes into account thrust computation, hydrodynamic forces and rotational dynamics, and updates the state. So for each time step of the simulation, we manage to have all this data, letting us not only see what the boat would do, but during design moments, we can see if it's better to have more capacity or more weight to actually implement on the boat beforehand. For the dynamic simulator, we have chosen the Fossen 3 degrees of freedom, which is actually the industrial standard. It has been calibrated through CFD using ANSYS, but also for the motor, it's the same that we used last year. We've done an SGD, a stochastic gradient descent, to actually optimize the wattage that the engine is using to last year's. This model is used for route validation and forms the core of the digital twin. So without putting the boat in the water, we can see what the boat would do the day before. Here we can see the actual simulator iterating over 296 waypoints from the route. So the pathfinding algorithm has decided on 296 locations that the boat must follow, and we can see here in the next slide all the telemetry we have that's completely simulated without putting the boat on the water. We have a surge, sway and yaw rate together with the controlling variables there is. This simulator also takes into account the inertia, obviously, of the boat, but also the added water mass and some hydrodynamic damping for which we have used ANSYS. Also, there's a built-in analysis tool that helps us develop the boat during the design, so that we have actual feedback without having to build it, testing it in the water, and then going back again to the design desk.
So Agustin, as I told you, is our digital member. He's an AI assistant that is constantly learning from the team's interactions. During the day, he answers to the team's technical questions using the information from his knowledge base. And during the night, he analyzes conversations he had during the day. He generates structured notes, and he updates his memory. So every day, Agustin wakes up knowing more than the day before. During the race day, Agustin has two different modes. First is proactive mode, which consists on giving automatic orders to the pilot and also informs her of critical telemetry data, such as battery, speed, or drift. And in his second mode, which is the responsive mode, consists on answering to the pilot questions about general boat aspect. In naval engineering, to build structures as light as possible is crucial for building efficient boats. So in this case, we took inspiration from two different natural patterns. First would be the microstructure of the woodpecker's beak, which is a zigzag honeycomb pattern that has a very high absorption to impacts without the necessity of adding mass. And in the second place, there is the dragonfly's wing venation, which is based in the Bournois pattern and gets an optimal stiffness distribution with the minimal possible mass. So for the woodpecker's beak, we have used this pattern to build a sheet that supports both batteries, first and second, and we have made it with layers of fiber resin and the lightweight core, which is the woodpecker's beak. And for the dragonfly wing venation, we used it, as you can see, for the transversal ribs of the structure, which have been lengthened with this pattern. So this pattern is very efficient because the vein network reinforces only the parts that truly need stiffness, so that with very low mass we obtain the same rigidity. So here you can see this piece is the transversal ribs that is inspired in Bournois pattern, and it supports both the longitudinal structure and supports the cabin between some other things.
Then finally, what we have intended for next year is to everything we have done with the simulator and with the pathfinding algorithm to publish it open source, because we think that maybe here on the endurance it has capabilities that are not really applicable because it's a small stadium, but that it has like a strong implementation into offshore sailing and yachting. And our idea would be to actually publish everything open source and free to anyone, for anyone to fork and improve. And hopefully we're excited to form a community of students that are from here, from the Monaco Energy Boat Challenge, that make the simulator better and actually applicable to the whole world, and hopefully create an actually useful library. So the following steps would be, with the data we can get from here, debug and find actually the correlation there is between what we expected and what we really got. And then during August and September, debug and document all the code to finally publish it on the end of 2026. So thank you. This has been everything. We hope you've enjoyed it, and if you've got any questions, feel free.
Thank you for your presentation. I will now open the floor again to the jury for their questions.
Thank you for a really great presentation. A question about some of the biomimicry work that you did. When you were developing that, do you have any data for comparison with your sort of standard layup that you did maybe last year, or do you you can see what the performance of that is, but did you compare it to other techniques as well?
Last year we had a completely different structure. So this year the technical rules had to change to make them wider. So we just changed it completely. So the correlation is actually not direct, but still we can assure that last year's structure was like around 18, 19 kilograms, and this year's structure is 15 kilograms, being much bigger.
Thank you.
Yes, so first congratulations, because having teams coming with an open source is something I'm very delighted, and the whole jury, we are very sensible of it. So first of all, congratulations and thank you for that. One question regarding the twin, numerical twin. Could you give us an idea about, maybe you just have the measure today, the difference in between the simulation and the real measure, because that's always the struggling point.
Yes, we were expecting to have the data today to start comparing it, but we've had some problems with the hole that they've been flooded of water, so it isn't actually like a really comparable for us to do, and we've been like trying to solve the problem. But yes, like once we have data, we can actually reuse the same algorithm that we used for the SGD. That's our intention, to find the exact parameters, to actually find all the parameters for the boat, to make it more precise.
Thank you. And could you please share an idea about, okay, you want to leave it open source, but do you have an idea about what kind of people can use it to try to optimize their efficiency in their daily use case?
Yes, for our idea is to leave it open source, completely open source, and for where it will be like more useful, we think they will be like in offshore sailing, where, like, for example, we had like a 16 to 20% improvement going from Bilbao to the Canary Islands in simulations, and it's much more noticeable in those types of offshore sailing than this like close range distances.
Thank you.
Would there be any questions from the audience? Would anyone from the audience have a quick question? Thank you very much for your presentation. Thank you. So we proceed to our next presentation from Electra Unigi.
Hello everyone, my name is Matteo. I'm the head of Electra Powertrain Division, and today I am proud to present a project that represents a paradigm shift in the propulsion of our catamaran. Let's take a look at the core problem. In the previous Monaco Energy Boat class events, our boat drove the motor through a passive direct wire, and this cost us the impossibility to implement any sort of energy management during the races. The performance is degraded because every wave hitting the hulls causes the pilot's hand to shake, and this tremor is passed directly through the motor, causing an unstable thrust and wasting valuable energy. And one broken line in the throttle up until last year takes the propulsion with it. So we were running a powerful machine, but with zero filtering and zero fallback protection. So our solution was to insert one intelligent, safe, and energy-aware layer between the pilot and the inverter. And with this, we instantly delivered 3 benefits. The first is that we have the possibility to shape the command of the pilot according to a specific mission, extending the range per kilowatt hours. Then filtering the signal, the command from the pilot, delivering a clean and undistorted command to the inverter and the motor. And then this is a fail operational system because we implemented 3 different independent safety layers, which are a software watchdog, a manual bypass, and emergency relays that makes the pilot always in control of the boat, even on an electronic failure. So this is the position of the ECU in our powertrain chain. So the command of the pilot is directly routed to the ECU, which is processing this signal and command the commercial off-the-shelf inverter. We have also another communication with to share data with our telemetry unit, which runs on a Raspberry Pi. And then we have some buttons for the pilot to switch between the different modes, and the signal lamp to display the status of the board on the dashboard for the pilot. Let's dive into the hardware. This is a 3D render of the board, which was designed in the Altium Designer and was fully assembled in our laboratory at the University of Genoa. The heart of this board is ARM-based microcontroller, the STM32. And we have galvanic isolation on every input-output, 2 communication with the CAN bus, 2 different sources for the throttle, digital and mechanical. Then, as I said, 3 independent safety layers, watchdog, bypass, and relay. Protection with TVS diode for protecting from ESD, and RC filter for signal conditioning. And then, as I said, signal lamps and buttons for the pilot. The microcontroller is the center of the board, completely shielded from external spikes. Then we have 3 different modular zones, which are the analog front end, the digital input-output, and the DC-DC power converter stage. So in this way, if a fault occurs, the damage is strictly contained in a portion of the board, and the microcontroller can continue its operation. Let's talk about the main innovation that we think that we take with this board. We have implemented at the moment 3 different control modes. The first one is the simplest because this is the manual, so the pilot stays always in control, and the board is only applying filtering for the noise and delivering a clean signal to the inverter. Then we have the cruise mode, where the pilot or the team on shore can send either a speed set point or a power set point, and the ECU is keeping it autonomously without requiring any micro adjustment from the pilot. And then we have the traction control, which is specifically designed for the slalom and the sprint races, because it maximizes the motor responsiveness and limited torque spikes, preventing propeller cavitation. The second innovation, as I already said, it is the failure operational safety chain, because this board operates in the control path of a moving boat, so it must be fail operational. And I discussed before about these 3 independent safety layers that guarantees that the pilot stays in control always, even on an electronic failure or loss of power. The third, since the racing catamaran operates in a harsh marine environment, we have switching harmonics, vibration, and so on. So we designed this signal conditioning chain based on TVS clamp and then RC filter and divider for signal processing to clean the signal and rescale it to the ADC. Then we have also galvanic isolation to prevent ground loops between the high power battery pack and this control logic. As I already said, this board features two independent CAN link communication. The first is for the communication with the inverter, reading the live data and enabling precise real-time control. Then we have a telemetry link, which is bidirectional to share data with the telemetry unit, and it's important for receiving a live strategy update during the race from the team on shore. And also these CAN buses are fully protected against ESD, transit, and faults. Here there is a picture of the first version of the board alongside the test bench that we built, the back-to-back test bench that we built in our laboratory for the test. The board then was tested also during sea trials, and now it is fully installed and operating in our boat. Here instead there is an Altium project, the overview of the Altium project, where on the left we have the full schematic, and on the right the PCB layout and routing. In conclusion, let's see how the ACU answer each assessment point of the innovation prize. First of all, novelty and uniqueness, because we replaced a direct passive link with an intelligent brain, an intelligent control layer, which is rare among the energy class boats. Problem solving, because we successfully filter noise, optimizing the power consumption of the boat. Market potential, because this is a modular architecture which is highly versatile and can adapt to, it's like a plug-and-play throttle-by-wire that can adapt to almost every little marine boat. Feasibility and scalability, because this is built with commercial off-the-shelf components, which are reliable, and of course it's also easier to scale for different input, to add multiple input and outputs. Proof of concept, because this is, as I already said, this is already installed and running on our boat at this edition of the Monaco Energy Boat Challenge. Thank you very much for your attention.
Thank you very much for your presentation. I will now open the floor again for the jury to ask some questions. Thank you.
Very nice, interesting application. Well done, all this exercise. But one key question is, what is the result of all this effort in numerical, quantitative approach? With all this type of thing, what is the effect on consumption, on something numerical?
The most satisfying aspect of this project is in the endurance performance, because we compared the performance that we had in last year endurance race with the test that we performed during our sea trials, and it is clear that the power consumption is way more constant than the other years, because the last year we calculated the set point, we set that to the pilot, and the pilot was constantly adjusting the position of the throttle. Now it is independent, and the pilot can focus just on the line, not on the throttle.
Do you have an idea about the market potential? What kind of market you can address with such a solution? I have an idea, but I want it come from you.
Okay, the market potential, it's more or less, I think that for these small little electric boats where you can put this brain in the middle to apply any sort of control that you want, also implementing different type of control. I'm thinking about also adding some steering sensor for controlling about the power based on the steering position. So it's modular and it's highly versatile, as I said. So I think that the market potential is high of this this project.
Thank you.
Would there be any more questions from the jury? No. And would there be any questions in the audience? Thank you very much for your presentation. So thank you for your enthusiastic round of applause. I would now like to welcome to the stage last in the Innovation Prize, Surge Methanol Foiling Team Twente. Thank you.
So hello everyone, we are Surge Twente, the first methanol foiling team, and we are charting a new course by the use of green methanol. This year we came to Monaco with a group of 22 students to prove a concept. To prove the concept that methanol is the future of the maritime and yachting industry. I am Balder, and next to me is Twan, one of our fuel cell engineers, and we will explain today what we do with green methanol and why is this the future in our vision. And if we talk about our vision is innovation to inspire. The last 10 years, we developed solar boats, developing more and making them the best as it can be. But this year we shifted. We shifted to a fuel that we think has the future, and that is methanol. 3% of total global emissions come from the yachting and maritime industry, and we think something should change. We should change something about the fuel consumption and the fuels we use.
Yes, so that leaves us by choosing the right fuel. When choosing a fuel, there are a couple things to look at. First of all, it's important that our fuel is compact. That means it has a low weight and a low volume. The next step is the versatility, meaning that it's safe to handle and easy to store and have nice logistics. And last part is the scalability. Scalability of the fuel to actually become the fuel for the upcoming decades. So that's why we look at. And of course, it's also very important that our fuel is carbon neutral. So let's look into the first fuel options, which is the traditional fuel we use nowadays. Current boats use heavy fuel oil. It's quite a thick oil, and it is actually a really good oil because it has a lot amount of energy. The energy density is really good. But the problem with the current fuels that the carbon intensity is really, really bad. 3% of the global emissions, just like Balder just said, is coming from these fuels. So these are not an option. The efficiency of these fuels are actually quite good. Another option is looking into batteries. Batteries are also being looked at, and batteries are really efficient, about 85 to 90%. But the problems with batteries is that their energy density is really, really low. So instead of shipping goods, you're basically just shipping the batteries. This can happen for smaller boats, but for really big maritime ships, this will cause lots of problems. So batteries, not exactly feasible. Another option, which I'm really looking forward to, is hydrogen. Hydrogen is carbon neutral because your emission is water, and it is quite good in the weight. So the energy per weight is quite good. But hydrogen in its normal form is gaseous. And the gaseous form of hydrogen means that it takes up huge amount of volume. So same with batteries. The vast amount of the cargo of your ship is the actual the fuel. And besides that, hydrogen is also really explosive. So handling it is not so easy, to say the least. What about methanol? The last option. When you produce methanol like we do, producing it in a green way, it can be considered carbon neutral. It's also quite decent in the energy density, and it's easy and safe to handle, because there's already a lot of logistics for it. It's basically one of the main chemicals in the chemical industry, and the efficiency is also quite good. So we believe methanol strives the overall best balance by choosing the right fuel. And we just not say that it's not just our opinion, but also the international marine organizations or other marine organizations say that methanol is the future for the maritime organization. So that's why we chose to transition to methanol. This year we actually built the first boat in this competition powered by methanol, which was really cool. So last year we built it and we produced our own methanol. Methanol can be produced in different ways. The vast majority of the current methanol is called grey methanol. And we use fossil fuels to make this methanol. But we can also do it differently. We can use green electricity to produce CO2 on one hand. We can capture that CO2 out of the air. About 0.04% of the air consists of carbon dioxide. And we can capture that out of the air. And we can also produce, we can also produce hydrogen. And hydrogen can also be produced through electricity, through electrolysis. So, and we can combine these two, the CO2 captured from the air and the hydrogen produced by electricity, and then we can produce methanol and water. So this methanol can then be used in our system. And I will explain a bit about how our system works. In our system we have a so-called reformed methanol fuel cell. And in our reformed methanol fuel cell we start with a mixture of methanol and water. This mixture then gets converted into the reformer through hydrogen and carbon dioxide. And the hydrogen then goes to a normal fuel cell, just like the hydrogen fuel cells, and ultimately produces electricity, water, and some CO2. But because we use green methanol, we can be considered carbon neutral. So just to summarize, in a reformer we produce make mainly hydrogen and carbon dioxide, and then the hydrogen goes to the fuel cell, where ultimately electrical power gets produced.
And this brings us to today, because by purely using a powertrain by methanol, we can sail. So this year we used a refurbished hull and adjusted it to our own personal uses. Then we put in our methanol fuel cell and an electrical system. This high voltage battery system this year functions as a buffer, because this year our methanol fuel cell can generate all the power we need to sail, so we capture it in the battery system, while we in the future want to tip the balance and create more power from the methanol cell and make the battery a bit smaller. Then we have our propulsion system that is below the boat. And as you already can maybe see on the picture, we don't only just sail, we also try to foil, and that's quite incredible. We have a quite unique hydrofoiling system, and we use special struts made by Xcore that are very unique in the market. Furthermore, we have an advanced control system with multiple sensors, sonars, and an IMU that capture all the data about the height above the water and accelerations of the boat to make it as stable as possible. And that all these components together make our first boat powered by green methanol, and that is Eclipse.
But, of course, we don't stop there. We continue to innovate in the upcoming years, and we try to keep on going to build our boat, make our boat better for these races. So next year we're going to be starting by building our own hull. Last year we've been designing this hull, but next year is actually the time to build it. So the next team members will have are quite busy with building this, but it will be really worth it. Another step is what we are really busy is the fuel cell. Current system is a consists of a fuel cell, reformed methanol fuel cell, but we're also currently designing our own reformed methanol fuel cell. This own fuel cell will have a lot more power and will also be made specifically for maritime usage. So a lot of these fuel cells are not specifically designed for maritime ships, but our fuel cell will specifically design it for the maritime organization. And with that, we also have the ambition to capture CO2 out of the air by using a carbon capture unit, which is also something which the maritime organization is really looking forward to. And with that, we want to keep on innovating and keep on inspiring the maritime sector, because we believe that methanol is the future, and that we can innovate and keep on making the maritime organization more sustainable. And this is our boat, so thank you for this presentation.
Thank you very much for your presentation. I will again open the floor to the jury for the last set of questions of the day.
Yes, first, congratulations, because being a pioneer is always full of tough situation. Yeah. And maybe if you could go back on the slide where you explained the process from producing the methanol to after having on board. I want to know the global efficiency of the whole drivetrain, at least to produce kilowatt hours out of the fuel cell. This is my first question. Second question, I want to know the life expectancy of the fuel cell, because we all know that, and I am the former CEO of a company, one of the world leaders in hydrogen, so we want to use a reformer in our fuel cell, but we were struggling with the quality of hydrogen that was decreasing a lot the lifespan of the fuel cell. So that's my second question. If you can answer those two questions after, I think the jury might have others.
Okay. So starting maybe with the question about degradation. A lot of the degradation is because of carbon monoxide. So the carbon monoxide goes to the fuel cell with the hydrogen, and there it can poison the catalysts which are in the fuel cell. And during the first step, the reforming step, besides hydrogen and CO2, of course, there are also some other chemicals that are being produced, and one of them is carbon monoxide. But by increasing the temperature used in the reforming, we emit less carbon monoxide, and that decreases the degradation of the fuel cell. But still, carbon monoxide can cause some degradation to the catalyst in the fuel cell, and further research will be done to either improve the catalyst, decrease the carbon monoxide, and overall improve the less degradation. And what was the first question again?
The first question is the whole efficiency chain you're having.
Yeah. Our current system is, I don't have the exact number, but I think it's around 50%. And it
from where to where?
Total system.
So you are producing energy with green electricity.
Yeah.
Capturing the CO2.
No, for the fuel cell. So without the methanol production itself.
Okay. So and if you integrate the methanol production?
I don't have the exact numbers about the production method which I just said, because there are a vast amount of ways to produce the methanol, and also with the efficiency of our current fuel cell, there's also possibilities to increase that efficiency, but it's still a lot more efficient than combustion engines. But it's also a bit of a balance, because combustion engines don't have the catalysts that are being used in the fuel cell, and which are in the fuel cell, the catalyst. So it will be interesting to also do like a techno-economic LCA assessment to see the balance between the combustion engines and the fuel cells.
That's why we're expecting a bit. And also another way to answer my second question that you answer first.
Yeah.
Do you have the purity of the hydrogen coming out of your reformer? Is it a 99.997 or is it less than that?
this step, like the hydrogen and CO2.
Yes, what's the quality of hydrogen before you are entering the fuel cell?
Yeah, it depends a bit, but it's around 50 to 60%.
Okay.
And that's also because in the fuel cell, you don't want to have it at near to 100%, because there can have a problem where there's too much hydrogen in the system, and the transition from the hydrogen to the electrical power will not be completely good, and then it will take protons from other systems in the fuel cell, and that can damage the whole system. So all the PEM fuel cells, the fuel cells that are being designed, are never designed for 100% hydrogen.
And maybe to comment quick on the efficiency, yes, the system is a bit less efficient than pure hydrogen systems, but we tackle also the handling issues, because methanol is a liquid at room temperature, so we can the bulking of ships, the usage in tanks, the sizes of tanks are very different. We don't have the leakage with hydrogen, we don't have the explosivity with the hydrogen, so we take away the dangers, and yes, we make it a bit less efficient, but we also think that the handling part of fuel should be really important when we look at the future.
Definitely, but as we asked to all your colleagues before, we need numbers, you know. If we are a jury and we want to validate something, we need to have a clear number to take a decision. And that's a bit what we are missing. That's why we are trying to ask the question, because we definitely need to have the numbers to take decision. Okay, do we have other questions?
I totally agree. It's a proof of concept. We're the first ever to do this, so the numbers will follow in the coming years when we have done more research and focus more on the efficiency and the status of the systems.
I'm sorry, I have a very naive question. I'm not an expert. Who would be your customer?
So if we look currently at the maritime sector, like large vessels, large owners are looking at methanol as like a way to reduce carbon dioxide. Currently, they're investigating implementing it in current motors to reduce the emissions. So that's the first step. And the fuel cells are a bit better suitable for smaller vessels. But methanol, within cooperation with doing research into implementing it motors and doing research for the fuel cells for smaller boats, there is a market open for it.
And just also to clarify, the whole jury is full supportive to what you are doing. But if we really want to highlight you, we need those numbers.
I think also from an industry perspective, another issue was always basically the refueling infrastructures, especially when you talk about shipping. Do you know where the industry is going on that? Is there any plans to have the infrastructure? Is there already some stations available? Like the new ships that are coming in from the big liners like Maersk, MSC, are they starting to implement this solution? Because I'm sure they've been studying something like this.
So for the refueling, like we are from the Netherlands, so in the port of Rotterdam, it's a big chemical harbor as well. Like my colleague said, methanol is used in other industries. And not really in the transport industry, so there is a lot of infrastructure already in place to do bulking with ships, refueling, and actions like that. So there's already infrastructure in place. Another benefit is that it is liquid, so it can already also be implemented in current fuel infrastructures. So that makes it easier to implement into the real world.
Thank you very much, everyone, for your questions. Sorry, I believe there might be an audience question. Two. Can go fast.
Thank you. Paolo Schito from Politecnico di Milano. I have one question regarding, you are speaking about a new, let's call it engine, a new storage of energy. Can you compare it with the traditional ones, let's say internal combustion engines, and with the electric ones? So in terms of space, complexity, and how much this will affect the boat layout or the ship layout?
Do you mean a balance, a difference between fuel cells and combustion engines, or?
No, the size of all these objects. So if you remove an internal combustion engine, could you put the fuel cell? And if you remove the fuel tank, can you put the methanol tank? If this is compatible, you need larger spaces, smaller spaces.
Yeah.
The weight of the system, fuel plus engine, is comparable. So if you can
to traditional fuels?
Or with the electric and battery system.
Yeah.
So if you can argument it a little bit.
What maybe is interesting for everybody in the audience is after this presentation, look up a chart between of all the different different fuels, and you'll see you have on the axis you have the volumetric energy density, and on the x-axis you have the kilogram density. And batteries are really low in their energy densities, and current fuels, like the fuel oils, are really, really high. And the methanol is somewhere like halfway between those two. So it's a little bit less in energy density than current heavy fuel oils, but those have the carbon emissions. But they're way more energy dense than, for example, batteries and hydrogen. So that's one of the main reasons why we chose for methanol, because it's really a lot more energy dense than those alternatives. Yeah. 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 So our system currently it produces it's capable of producing 5 kilowatts, and it weighs about 70 kilograms. And the size, somewhere like this. Yeah.
Thank you. One more question.
Yes, thank you. Really interesting approach. Just a couple of comments, because many times the evil is in the details, and I think the suggestion to give some numbers is proper, even in the evaluation of the LCA of the different technologies that you compared in the beginning. It could be interesting to have some numbers, not just plus, minus, and the average. But the question is about the preparation of methanol. You know that they use probably the harshest part to produce methanol, because you take the CO2 from the air, which is quite expensive and quite difficult to do. You take green hydrogen, which is probably the worst case in cost and complexity. But you know that you have a lot of methanol available even from waste and from agricultural waste and what else, which is considered CO2 neutral as well. Have you tried the numbers with this kind of supply instead of the more technical relevant that you suggested, or not?
Yeah, I can't give you the exact numbers, but just like you just said, the main reason why the green methanol can be more expensive is one, the electrolysis of the green hydrogen, and exactly the carbon capture which used. Another alternative which you just mentioned was the biomethanol, and you can also produce it through biomethanol. Currently, there's also looking into producing it directly with methane and CO2, and then you don't have the green hydrogen cost. But producing methanol through biomethanol, there's also increasing in lowering those costs. So eventually, they will drop. And also through policies, taxes on fossil production of methanol, at some point they will be comparable, but it also depends a lot on political decisions, etc. So, but currently it's indeed the case that green methanol is more expensive than grey methanol. Yeah.
Thank you very much. So I would like to say a big thank you for all the teams who have worked hard in submitting the innovation prizes and all your efforts that have gone into these presentations and the months of work before. So to close the session tonight, I would like to thank you all for attending and being part of the Monaco Energy Boat Challenge 2026. And also I would like to invite you to the meeting room to enjoy and participate in the eSport Championship qualifiers taking place from 7 o'clock onwards. And to conclude the session, I would like to ring the bell. I think I'm going to put the microphone down before I do it.
Piliers de notre société